So far, we've learned how to deploy applications, scale them, configure them, and store data. But there is still one important question. How do users access our applications from outside the Kubernetes cluster? In this episode, we'll learn about load balancers, Ingress, NGINX Ingress Controller, and TLS. By the end of this video, you'll understand how internet traffic reaches your pods. Earlier in the series, we learned about services. ClusterIP services are great for communication inside the cluster. However, they are not accessible from the internet. A user sitting outside the cluster cannot directly reach a ClusterIP service. We need an entry point that allows external traffic to enter Kubernetes. One solution is a load balancer service. A load balancer receives traffic from the internet and forwards it to a Kubernetes service. This works well when you want to expose a single application. The challenge appears when you have many applications. Creating one load balancer for every application can become expensive and difficult to manage. This is where Ingress becomes useful. Instead of creating multiple load balancers, we can use a single entry point. Ingress allows us to route traffic based on host names or URL paths. For example, app-a.company.com can go to application A, while app-b.company.com can go to application B. One entry point, multiple applications. An Ingress resource by itself does nothing. Kubernetes needs a controller that understands and applies the routing rules. One of the most popular options is the NGINX Ingress Controller. The controller continuously watches Ingress resources and automatically configures traffic routing. Think of the Ingress resource as the configuration and the controller as the engine that makes everything work. In production environments, we rarely expose applications using plain HTTP. Instead, we use HTTPS. HTTPS uses TLS certificates to encrypt communication between users and applications. This protects passwords, personal information, and API traffic from being intercepted. Ingress controllers can also manage TLS certificates and HTTPS termination. Before we start the hands-on section, let's quickly talk about TLS. So far, we've focused on routing traffic, but in production environments, routing alone is not enough. We also need to protect the traffic. On the left, we have plain HTTP communication. Traffic travels across the network without encryption. Anyone intercepting that traffic could potentially read sensitive information. On the right, we have HTTPS. HTTPS uses TLS certificates to encrypt communication between users and applications. This protects passwords, authentication tokens, payment information, and other sensitive data. One of the advantages of using an Ingress controller is that it can handle TLS termination. Users connect securely using HTTPS. The Ingress controller manages the certificate and receives encrypted traffic. Then it forwards requests to the applications running inside Kubernetes. For this demo, we'll keep things simple and use HTTP. Our goal is understanding routing and traffic flow, but in real production environments, TLS is commonly configured at the Ingress layer. Now, let's build our first Ingress and see how the traffic flows through Kubernetes. TLS. Enough theory. Let's build a working Ingress. We'll deploy an NGINX application, expose it with a ClusterIP service, create an Ingress resource, and route traffic through the NGINX Ingress Controller. Before we start, let's organize our project. We'll create a dedicated folder for this demo and keep each Kubernetes resource in its own YAML file. This is the same approach used in real Kubernetes environments because it makes configurations easier to manage, review, and deploy. As always, all files from this episode will be available in the GitHub repository for the channel. Before creating an Ingress resource, we need an Ingress controller. Remember that an Ingress by itself is only a set of routing rules. The controller is the component that reads those rules and applies them. Minikube includes an NGINX Ingress Controller add-on, so we'll enable it now. Let's verify that the controller is running. If the controller is healthy, Kubernetes is now capable of processing Ingress resources. We can see 3 resources here. The important one is the controller itself. You may also notice 2 admission jobs. Their status is completed. That's completely normal. These jobs run during the installation process, perform their configuration tasks, and then exit successfully. Now let's deploy a simple NGINX application that will expose through the Ingress controller. Our application is now running inside the cluster. However, nobody outside Kubernetes can access it yet. Here we're defining how traffic flows through the service. The service listens on port 80 and forwards requests to port 80 on the application container. In our case, NGINX is already listening on port 80, so both values are the same. It's common to see different values in real applications, but for this demo, we'll keep it simple. The most important part is the service type. We're using ClusterIP, which is the default service type in Kubernetes. A ClusterIP service is only accessible from inside the cluster. That means pods can reach it, other services can reach it, but users on the internet cannot. If someone opens a browser on their laptop, they have no way to access this service directly. And that's exactly the problem we're trying to solve in this episode. Right now, our application is running and our service is working, but everything is still internal to Kubernetes. The next step is creating an Ingress resource that will expose this service to external users. How do we allow external users to reach this service? This is our Ingress resource. Think of it as a set of traffic routing rules. Earlier, we created an internal service. Now we're defining how external traffic should reach that service. We're creating an ingress called NGINX Ingress. This tells Kubernetes which Ingress controller should process this resource. Earlier, we installed the NGINX Ingress Controller. That's why we're using NGINX here. This is the hostname users will access. Whenever somebody sends a request to demo.local, this ingress rule will be evaluated. The slash means every request that starts at the root path. In more advanced configurations, you can route different paths to different applications, but for this demo, we'll route everything to the same application. Finally, we define where the traffic should go. Requests arriving at demo.local will be forwarded to NGINX service on port 80. The service will then distribute traffic to the pods. So the flow is very simple. Traffic enters through the ingress forwards traffic to the service, and the service forwards traffic to the pods. Kubernetes has registered our ingress resource. The routing rule now exists inside the cluster. The last thing we need is to make our computer resolve demo.local to the Minikube cluster. Our ingress is already configured inside Kubernetes. However, our computer still doesn't know where demo.local lives. We need to obtain the Minikube cluster IP and associate our host name with that address. In a production environment, this would normally be handled by a DNS provider. For this local demo, we'll use our host file. Let's take a moment to understand what we just did. Every time you type a website name in your browser, your computer needs to find the IP address associated with that name. Normally, this process is handled by DNS servers on the internet. For example, Google.com resolves to one or more IP addresses. In our local Kubernetes environment, there is no public DNS record for demo.local. So we need to create that mapping ourselves. This command opens the host file. The host file is a local DNS table stored on your computer. It allows us to manually associate host names with IP addresses. By adding this line, we're telling our computer, whenever someone tries to access demo.local, send the request to 192.168.49.2. And in our case, that IP address belongs to the Minikube cluster. So before this change, our browser had no idea where demo.local was located. After updating the host file, our computer can find the Kubernetes cluster and send traffic to the Ingress controller. Let's verify our ingress one last time. We can see that Kubernetes has registered the hostname demo.local and the routing configuration is active. At this point, everything is connected. The only thing left is testing the application from a browser. That's not what we expected. The request is unable to reach the application. Let's try another test. At this point, everything looks correct from the Kubernetes side. So before changing random configurations, let's see if other people have experienced the same problem. Let's type on Google, Ingress not working on Mac M1 host machine. Interesting. I found a GitHub issue in the Minikube repository with exactly that title, and the symptoms look very familiar. This user says that Ingress is enabled, the hostname is configured, and the host file was updated, but requests simply hang and never reach the application. Let's keep reading. Here's another user reporting the same behavior while running Minikube with the Docker driver on Apple Silicon. That sounds very similar to our environment. Now this comment is interesting. A Minikube contributor explains that when using Docker or Podman drivers, Minikube tunnel is required for Ingress to work correctly. So that's definitely something we should test, but let's continue reading. This comment caught my attention. The user says that Minikube tunnel worked, but there was one additional detail. Instead of pointing the host file to the Minikube IP address, they mapped the hostname to 127.0.0.1. Earlier in this lab, we configured 192.168.49.2 demo.local, which seemed perfectly reasonable. But according to several users, that approach doesn't work correctly on macOS when using the Docker driver. So rather than guessing, let's follow the recommendation from people who already solved the problem. We'll keep the tunnel running, expose the NGINX Ingress Controller through a LoadBalancer service, update the host file, and see if that fixes the issue. Let's try it. Before making any changes, let's inspect the service created by the NGINX Ingress Controller. This is the component responsible for receiving external traffic before it reaches our applications. Notice that the controller is currently exposed as a node port service. Based on what we found in the Minikube issue, we're going to expose the NGINX Ingress Controller using a LoadBalancer Service. Notice that we're not changing our application service. Our application remains behind a ClusterIP service. We're only changing how external traffic reaches the Ingress Controller. Let's verify the change. We can now see that the controller is exposed as a LoadBalancer service. It may take a few moments while Minikube assigns the external address. Next, we'll start a Minikube tunnel. The tunnel creates a route between our local machine and the Kubernetes cluster. Keep this terminal running while we continue. Perfect. The controller now has an external address that our local machine can reach. Earlier, we mapped demo.local to the Minikube node IP. According to the community findings, that doesn't work correctly on macOS with the Docker driver. Instead, we'll map the hostname to localhost and let the tunnel handle the routing. Our hostname now resolves to localhost. Let's see if the community was right. We updated the controller, we started the tunnel, we corrected the host file. Now let's test the application again. Success. The request is finally reaching the Ingress controller. The controller evaluates the routing rules. Traffic is forwarded to the service. The service forwards the request to the pods, and our application responds successfully. Before we continue, there's an important detail I want to clarify. The issue we just experienced is not a Kubernetes problem. It's not an Ingress problem either. It's actually related to how networking works in different environments. On Linux, things are much simpler. The Minikube node IP is directly reachable from the host machine. There is no additional virtualization layer between the operating system and the cluster. Because of that, you can use the output of Minikube IP directly in your host file, and everything works as expected. In cloud environments such as AWS, Azure, or Google Cloud, this problem doesn't exist either. When you deploy an Ingress controller, it is usually exposed through a LoadBalancer service. The cloud provider automatically creates a public endpoint. That endpoint can be a public IP address or a DNS name. Users simply connect to that endpoint and traffic is routed to Kubernetes. Our situation is different. Docker Desktop on macOS runs containers inside a Linux virtual machine. That means the Minikube node lives inside another networking layer. Even though Kubernetes reports an address like 192.168.49.2, the address is not directly reachable from the macOS host. That's why our requests were timing out. To solve the problem, we actually performed 3 different actions. Each one solved a different part of the connectivity issue. First, we expose the NGINX Ingress Controller through a LoadBalancer service. This created an entry point that Minikube Tunnel could expose to our local machine. Second, we started Minikube Tunnel. Remember that on macOS, Minikube runs inside Docker Desktop, which itself runs inside a Linux virtual machine. The tunnel creates a network path between our host machine and the Kubernetes cluster. Finally, we updated the host file. Earlier, we pointed demo.local to the Minikube node IP. After researching the issue, we learned that on macOS with the Docker driver, the hostname should point to localhost instead. The tunnel then takes care of forwarding the traffic to the cluster. Once all three pieces were in place, traffic could finally reach the application. And this is probably the most important lesson of the episode. Kubernetes was working correctly the entire time. The pods were healthy, the service was healthy, the Ingress configuration was correct. The real issue was the networking layer between the host operating system and the cluster. Understanding where traffic flows and where it can be blocked is one of the most valuable troubleshooting skills you can develop in Kubernetes. Great, our application is finally working. The request reaches the Ingress controller, the service, and ultimately the pods. But before we finish, I want to spend a few minutes understanding something we used during the fix, the LoadBalancer Service. We changed the NGINX Ingress Controller from node port to LoadBalancer. But what exactly did that change do? The answer becomes easier when we look at how Kubernetes applications are commonly exposed in production. Users don't connect directly to pods. They don't connect directly to services either. Instead, traffic usually enters through a load balancer. The load balancer becomes the public entry point. It forwards traffic to the NGINX Ingress controller. The Ingress controller then evaluates routing rules and sends traffic to the correct application. This architecture gives us two major advantages. First, we only need one public entry point. Second, a single Ingress controller can expose many applications. In this example, one load balancer can expose 3 different applications. In real environments, it could be dozens or even hundreds. That's the theory. Now, let's see what a load balancer service actually looks like in Kubernetes. We'll create one ourselves and compare it with the ClusterIP service we've been using throughout the episode. Before creating a load balancer service, let's look at what we already have. This is the service we've been using throughout the episode. Notice that its type is ClusterIP. ClusterIP is the default service type in Kubernetes. It allows communication inside the cluster, but it doesn't expose the application externally. That's why we needed Ingress earlier. This service is very similar to the ClusterIP service we created earlier. The selector is exactly the same. It's pointing to the same NGINX pods. The port configuration is also the same. The only difference is this line, type load balancer. This tells Kubernetes that we want external access to the application. Let's create the service. Kubernetes will now create a second service pointing to the same pods. Now we have 2 services, both point to the same pods, but they serve different purposes. The ClusterIP service is intended for internal communication. The load balancer service is intended for external access. Let's inspect our load balancer service. At first glance, it looks similar to the ClusterIP service we've been using, but there are a few important differences. First, notice the selector. The service is targeting pods with the label app equals NGINX demo. That's exactly the same application we've been using throughout the lab. Here is the most important line. The service type is load balancer. This tells Kubernetes that we want this application to be reachable from outside the cluster. These are the actual pods behind the service. Notice we have 2 different IP addresses. That's because we deployed 2 replicas earlier. The service automatically distributes traffic between them. Here's something very interesting. Even though we created a load balancer service, Kubernetes also assigned a node port. That's because a load balancer service is actually built on top of a node port service. In other words, load balancer includes node port underneath. Traffic first reaches the load balancer. The load balancer forwards traffic to the node port. The service receives the request, and finally the request reaches one of the pods. Notice something interesting. Our load balancer service was created successfully, but the external IP is still showing as pending. Why? Because Kubernetes itself does not create load balancers. Kubernetes only requests one. In a cloud provider like AWS, Azure, or Google Cloud, the cloud platform would detect this request and automatically provision a real load balancer. Since we're running locally with Minikube, there is no cloud provider available to create one. Minikube Tunnel is acting like a cloud provider. It watches load balancer services and provides an external address for them. This allows us to simulate cloud behavior on a local machine. Perfect. Our load balancer now has an external address. The service is reachable from outside the cluster. Notice that we're not going through an ingress. We're accessing the application directly through the load balancer service. This is the key difference. A load balancer can expose an application directly, but an ingress allows a single load balancer to expose many applications through routing rules. What we just tested was a direct load balancer, but in production, the more common pattern is placing a load balancer in front of an ingress controller. Earlier in this episode, we actually built the architecture on the right. We created an ingress, we installed an NGINX Ingress Controller, and during troubleshooting, we exposed the controller using a load balancer service. So by the end of the lab, we were already using a simplified version of this production architecture. This is why Ingress and load balancers are often used together. The load balancer provides external access. The Ingress controller provides intelligent routing. Together, they create a scalable way to expose applications running in Kubernetes. We now understand what a load balancer service is and why we needed it during our troubleshooting process, but there is still one important question. If a load balancer can expose an application directly, why do we need Ingress? Let's see that in practice. Earlier in the episode, we were exposing a single application. Now let's simulate a more realistic scenario. Instead of using a single service, we're going to create multiple services and expose them through the same Ingress controller. Now I'm creating two internal services. app-a-service will represent our first application route. app-b-service will represent our second application route. For simplicity, both services point to the same NGINX-demo pods. In a real environment, each service would usually point to a different application. I'm going to remove the original NGINX service. We use this service for the first Ingress example with demo.local. Now I want the final demo to be cleaner, so we'll replace it with two new services, one for app A and one for app B. Then we create the new Ingress resource. This Ingress has multiple routing rules. Requests for app-a.local will be sent to app-a-service. Requests for app-b.local will be sent to app-b-service. Same Ingress controller, multiple host names, multiple routes. Let's verify it. Now we can see multi-app ingress with two hosts, app-a.local and app-b.local. This means Kubernetes registered both routing rules correctly. Since this is a local demo, we need to add both host names to our hosts file. We map app-a.local and app-b.local to localhost because Minikube Tunnel is handling the traffic. This allows our browser to resolve both names correctly. Let's test the first route. I open app-a.local in the browser. The request goes to the Ingress controller. The hostname matches app-a.local. Then the Ingress forwards traffic to app-a-service. Now let's test the second route. I open app-b.local. This request uses the same Ingress controller, but a different routing rule. This time traffic is sent to app-b-service. This is the key concept. One Ingress controller can manage multiple host names and route traffic to different services. In this demo, both services point to the same NGINX pods for simplicity. In production, each service would normally point to a different application. This is why Ingress is so useful. One entry point, multiple applications. Let's quickly review the most important concepts from this episode. First, a service alone is usually not enough when users need to access an application from outside the cluster. That's where Ingress comes in. and Ingress acts as a smart routing layer. It evaluates requests and sends traffic to the correct service. To work, an Ingress always needs an Ingress controller. In our case, we use the NGINX Ingress Controller. Throughout the episode, we followed the complete traffic path. The user sends a request. The request reaches a load balancer. The load balancer forwards traffic to the Ingress controller. The Ingress controller routes traffic to the correct service. And finally, the service forwards traffic to the application pods. We also learned an important architectural concept. A load balancer can expose a single application directly, but when we combine a load balancer with Ingress, one entry point can expose many different applications. This is one of the most common Kubernetes architectures used in production environments. And finally, remember the lesson from our troubleshooting session? Kubernetes was working correctly the entire time. The issue was the networking path between our machine and the cluster. Understanding where traffic flows and where it can be blocked is one of the most valuable skills you can develop as a Kubernetes engineer. And that wraps up our journey into Kubernetes Ingress and load balancers. Today, we learned how applications are exposed outside the cluster. We saw why services alone are not always enough. We learned how Ingress provides intelligent routing. We installed an NGINX Ingress Controller. We explored how load balancers and Ingress work together in production environments. And most importantly, we walked through a real troubleshooting scenario and learned how to follow the traffic path step by step. But if you've been following this series closely, you may have noticed something. Every episode adds more YAML files, deployments, services, config maps, secrets, volumes, Ingress resources, and as applications grow, managing all of these files manually becomes increasingly difficult. In the next episode, we'll solve that problem with Helm. Helm is often called the package manager for Kubernetes. It allows us to package Kubernetes applications into reusable charts. Instead of managing dozens of YAML files individually, Helm lets us deploy and manage entire applications with a single command. We'll learn what Helm is, how Helm charts work, how to install applications, and how to manage releases. If you want to work with Kubernetes in real-world environments, Helm is a tool you will use constantly. If you enjoyed this video, don't forget to like, subscribe, and share it with someone learning Kubernetes. I'll see you in the next episode.